Record. Okay, so we're on the Sunday night online office hour. We're going over number 3. So what you can see up here on the right is we needed to find out omega, so we figured out that's just an alpha dt. We're just simply integrating. So at 1 second, then omega would be 0.1. At 4 seconds, it would be 0.4, because this expression right over here is what we have for omega, and then we just have to integrate it again. And we did all this in a big for loop, right? So we're going to count with an n, we're going to set up t, so that might be something like, n minus 1 over 10, and then would go 0.1 second, 0.2 second, etc. And then we said we could just define the omega here, and then we can do our theta. So we're doing all this within our loop. Okay? And you can do that a for or a while, and there's some slight variations of how you can do this. So now we're talking about the r, and the r is going to start out here at 3, and that's going to be plus 3i, like what people had typed into our chat box. So it's going to be a plus 3i, and then how much does that move in? Right? What is it going in? Like at 1 second, then what's r going to be? Yeah, so Will's saying 2.5, and essentially we're doing the same thing, right? What do I know about the acceleration of you walking across there?
81.
Right. Well, up here I said it was constant, right? So what does that mean about a rel? Yeah, so a rel is 0. Are there questions about that? Because it's just me walking along the line. I'm walking at a constant speed of 0.5 towards the center until I get to the other side on the dotted line. Okay. So the a rel is going to be 0. And then if I want to know the distance along there, right, if I have velocity and I want distance, I just have to integrate again. Right? So for the v rel, basically then I've got that ds, I'll call it, so that's the distance, is equal to v dt as I'm moving across there. So there's a couple ways you can look to figure that out. Did anybody get an expression of how you're going to define r then at the end? Yeah, you're going to do VT, okay? But how are you starting out? We're starting out at plus 3. So how am I going to make it so that I get to, when would I get to the very center? At what time? Everybody understand my question? I'm saying, when will you get to the very center? Okay. Jason's saying 6. So Jason, how'd you figure that out? Yeah, just like what Will's put is a v times t, right? So it's, since I'm going 0.5 meters per second, and it's all constant, that at the, at that instant of 6 seconds, I'm going to be at the center. So I can write that as 3 minus that velocity that I gave you, right, times t. Okay, and remember, if I'm going to put this over here, I need to do an r sub n, because I'm going to do it at each time, and I do that so that I can plot it out easier in the end. Again, there's different ways you can do a function or something like that as well, but I always just kind of like doing this, because then I can really just look at each individual term, and I, so if I'm going to like debug your, that's not looking very good, is it? This is going to be minus v times t. That's not looking any better. Sorry. I'm going to put it over here. So r of n is going to equal then 3, which was our initial one. And it'd actually be more clever if you did like an r naught or something, and then you could define that up above. But for this case, we'll just do it like this. Okay, and I'm just going to scribble that guy out. Okay, does that make sense, everybody? Are there questions there? So it's all within a loop, and I try to make, most of the stuff's constant, so it shouldn't be too hard. But I could have made it vary with a lot of other stuff too, right? It didn't have to just vary, be a, just a constant for these, but you've got the MATLAB stuff to work on more intricate stuff, so hopefully this isn't too bad compared to what you're doing in there. Okay. Aaron, it looks like were you trying to talk there? Because I can't hear you.
No, I'm okay right now.
All right, hold on. Maybe I got something set up wrong. Hold on. Okay, say again.
I said I'm okay. I think my speakers are too loud, so you're probably hearing yourself.
Okay. Is this too? Am I talking too loud for everybody else? Do I need to readjust my thing somehow? Okay, good. All right, so then we've got the R, we've got the omega set up, right? And we know the A rel. So really we know all of these terms now. Okay. And then which direction is the omega in? Yep, same as alpha. So we've got that as being like a k hat or a z. And then which direction is the R vector in? Yep, so it's in the I. And then after 6 seconds, which direction is it going to be in? The minus I. Does that make sense, everybody? Because by then, this number is going to go to negative, right? And that should make all right sense to you. Okay, and this R is really just what's telling you what the path is going to be, right? So you really just have to figure that R out, and then you're going to do R cosine theta and R sine theta through time to then figure out what your path's going to look like. And I don't remember if it was in office hour, if we mentioned it in class. What do you think the shape's gonna end up looking like of the path if you look at it from over the top? Yeah, it's going to end up being a spiral, okay, as you go closer and closer in towards the center. Okay, so the omega and the alpha are both in the k hat direction. The R is going to be in the x direction, so you do a cross product there, right? And in fact, you kind of know which direction the normal, right? Which direction is this first one going to be in? Let's just do it sort of towards the beginning. Which direction is that term going to be in? Yeah, so it's a minus I, right, in towards the center at the beginning, okay, because that's our normal acceleration. Okay, then how about this term? Which direction is that term going to be in at the beginning?
Positive Y.
Yeah, it's going to be positive y because that's our tangential, right? Positive little y. That's our tangential term, right? And then the trickier one is going to be the Coriolis term, right? So that's going to have at first the omegas in the k hat, right? And then the v rel at first is in the minus I hat. Okay. So Alex, can you mute your thing? Because I think you're typing or something's coming through.
Yep.
Thank you. So then the k cross I, right, is going to be, k cross I is plus j, right? But then we have a minus sign, so the Coriolis term is going to be in the minus j hat. Okay, and you can look at that because it was going that way, and then due to that rotation, it's going to make it go that way. So it's in the minus little y hat. Okay. So Megan, were there other parts of this that were confusing for you? Okay. And which part was that? Just so I know for next time, which part was the most difficult for everybody on this?
Yeah, MATLAB for sure.
Okay. Um, great. Oh, it's you get to choose that, Matt. So so I just put 1 to 50 because then I was just going to go to like 5 seconds. So you can make that to whatever point you need. I might just start with some sort of number like 100 or whatever, and then I'll figure it out. Really, I mean, how far is it going across? How long does it take to go all the way across?
Just to clarify, what is TN?
Tn is the time at counter n. So like t sub 1 would be 0 seconds, and you get to set that up, right? So I would set something up like let's see, so I might say like I did there, where Tn is going to equal. And like I was saying, there's different ways you could do it. Like one way I'll sometimes do it is n minus 1, divided by whatever I want to call it. I don't know, del T or something like that. But that would be, maybe that's a 10 or a 20 or 100, right? So if it was 100, then each time it would start, if it was 100, it would start with 0, and then it would go to 0.01, and then the next n would be 0.02. Does that make sense for you?
Yeah, that makes sense.
Okay. So the reason, remember, that I do it this way is because I then can say plot T, comma, omega, right? And then because those need to be the same, the same number within there. Okay.
And for your theta, is that integral dw alpha dt that you derived on the right there. Yeah.
Yeah, I would use this one here. Okay. And then we also had a question about the AXYZ and the A capital XYZ. So this one that I've just found, with how come that's not working? Hold on. Oops. Can you guys still hear me?
Yeah.
Okay. My pen's just not working. Hold on for a second. Maybe I clicked on something down here. Okay, so this whole term, why is that not working? So all of this stuff that we did down here, right, is then what frame, what coordinate system is all that in?
Maybe in the little x, little y.
Yeah, so one question that I think Jason was asking, right, is what is those differences when we go about it? And really all you have to do is, like we talked about, I think it was Monday, where I'm going to have a certain AX from this thing, right? I'm going to get some sort of answer of AX is going to be in this direction, right? So that's going to be one component, and then I have another component in this little y direction. Well, then once I get that, I just have to say, well, how much of that's in the capital X1, right? And that was cosine theta. And then how much is in the capital Y? That's going to be a sine theta. And then we look at it from here to here, right? Do you guys remember us doing that?
Yeah.
So then in the wider, how much of this is in the capital Y? Well, that's going to be in the, in the cosine one, and then how much of it's in the capital X? It's a minus sine theta. So all you're doing now is finding it in the little XYZ and then transforming it into the big XYZ. Okay?
Mm-hmm.
Any more questions on this one? Okay, who else has got some questions? Okay, so for this first problem up here, right? Let me see here. So if we look at this one, right, then it says we've got this curved slender bar OC, and that one's rotating, as you see, at a constant value of 2 radians per second in the direction shown. Using the rotating analysis, right, on this one, how do we decide, or why do we tell you to do it with respect to OC, right? So we actually gave you a little hint on there, right? So for that one, does it make sense to everybody that you would want your rotating system to be with the curve bar?
Mm-hmm.
Okay. So then for the velocity B, we're going to do just like we've done before, where we're going to try to do now, and sorry, I'm having some sort of weird issue with my pen, where I can do it with my mouse, but I can't use my pen at the moment. So let me see. I may run downstairs to see if I've got another pen in a second here. But if we look at this one, then what we're going to be trying to do is figure out, like we've done before, where we're going to figure out the velocity of B, right? So we're going to figure out the velocity of B. We're going to do that by first trying to figure out, so now I'm going to see if I can do it just in this, maybe I can do it, shoot, it's like my pen just died. Okay, so with respect to O, right? So we're going to do it with respect to O at first. So does O have, does the velocity of B have a rel term with respect to point O?
Yes.
Yeah, and if everybody can see, right, then it's got one that's going to be going in that kind of X direction, right? It's constrained at that instant in time. It's going to be moving either left or right. So that's our VREL term. And then we also have the omega, which is attached to that circular one, right? So that we're going to have that omega, and it's going to be with a, when we cross the R, that R is going to go from point O down to B. So does everybody see that? That's VB equals omega of that bar OC crossed into R from O to B plus the VREL, and that VREL is going to be constrained to just move in the little I hat direction. Okay. All right, and then we're going to do velocity of B equals velocity A plus we have omega AB crossed into the R vector from A out here to B. Okay, so then basically we just have to set those two equal to one another, because the things we don't know are VREL and omega AB, right? Everything else we know. We know the omega of the bar OC. We know that VREL has to be in the direction of B, right? And we know the R from O to B. Does that make sense, Will?
Hey.
Yeah. Is there a question?
So can I ask a quick question?
Sure.
So essentially, you're finding two equations that involve velocity at B, and then you're setting those equal to each other. Is that correct?
Yeah, and that's the exact same thing we've done for pretty much all those questions,
Right.
all those problems from like 2 weeks ago, maybe.
Okay.
Does that make all right sense? Yeah, and actually, I should have even maybe said that when we were first starting. Is, hey, look, we've got two different rigid bodies, and they're connected through some sort of point, whether it's a collar or a slot or whatever. So, you know, I guess I usually say just go from link to link, and you're just connecting them all together. But maybe it's even a little more intuitive for people to say, look, we're gonna find whatever connection point there is, figure out velocity expressions for each one, and then set them equal. Okay, so we got another question there, right? Which is, for the acceleration part, do we need a v squared over r, right? So if you guys aren't talking, can you mute your mics if you're? We got a little background noise. So the question is, for the acceleration part, do we need a v squared over r term? And so if we look at, then this is going to answer your question as well, Will. If we look at how this guy is moving, let me see if I can do a spotlight here. Okay, so if we know, like right at that instant in time, right, so this thing's moving around a curve, and it's going back to that same argument we had with the curve slot, or if I'm going in some sort of curve motion, right, if I just have if I'm going around a racetrack or whatever, then let's say I'm going down right here, well, which way is my velocity when I reach that point? So if I was right here, my velocity would be going straight down. That would be my speed. And then maybe I have a tangential acceleration too. I don't know, right? So I could have a tangential velocity, and I could have a tangential acceleration depending on if I'm speeding up or not, right? So, but in this case, we don't know for the B if we're speeding up or not. Okay? But I know that right at that point, right, it just defines the velocity when I do, like, back to normal tangential coordinates. It has to be tangential to that curve. So my velocity is tangential, pointing straight ahead on the curve. So that's what my VREL is going to be. So, Will, does that answer your question? So wherever it is on that circular point, the VREL it's constrained. So if I have a straight slot, then I know I'm constrained to go in the straight direction, right? But when I'm on a curve one, then the velocity is always going to be tangent to the curve. Okay, good. And then Danny had the question about the acceleration part. Do we need a v squared over r term? And you do. And that was, we've been hitting you over the head with this a couple different times, right? Because we've had different slots, and then these, and then, the other one we had with the rolling thing. So I think we're just trying to get it across that, hey, anytime I've got a particle type of thing or a car or whatever that's going in a curved path, I always have a normal acceleration as well. So for any of these things with a collar or slot or whatever, I'm going to have a normal acceleration going in towards the center. And Danny, what am I going to use for V? What am I going to use for that V squared? What am I going to use for the V in that V squared over R expression, do you think? Yeah, it's going to be the VREL that you found from the velocity expressions. It's just going to be the VREL that we found from doing that first part. Okay, good. More questions? We haven't yet, Alex. So number 4 is, let me see here, and hopefully I can see maybe if my, that's this one, right?
That's the one I have questions about too.
Okay. So for this one, let me see. Gosh, I don't know why my pen's not working. Give me a second. I'm going to try to back out and then come back in. Give me a second. I'm going to do my control panel and see if I can get my pen working, because it certainly helps a lot. Touch. Okay, sorry here. Okay, well, I guess we'll just have to deal with the pen not working. So let me bring back up the... All right, we got a lot of bad feedback from something. Okay, so we're going to go look at this one, right? So what we have here, so we're going to need you guys to maybe, if you guys just joined, can you mute your mic?
I did not know what I was like. I had to talk to Sabrina about it because it was so simple that I was like trying to jump in.
So we can actually hear you, so don't say anything bad about me. I don't know who just joined in. So mute your mic, and we'll go. So basically for this one, let me open up the chat room again. All right, so Alec, you were asking about number 4, right? So the how that goes. All right, so basically if we look at, we've got the Z one, like what you were saying, that's going around, kind of around, let's see, what do I need to do? Let me go to annotate. So we're going around this way, right? So that one, like you said, is in the Z hat. And then this one, so it's going to be going down through there, right? So I agree with you in that that's going to be going in the, is that going to be in the plus Y or the minus Y?
It would be minus Y. Let's see. It's pointing. Actually, no, plus Y, right?
Yeah. So if you do your finger, if you curl your fingers in the way that that's going around, so that's going to be in the plus Y. Okay, so then if you do, so is anything making this top one, this omega, not change direction?
You mean like the Z-axis, or
Yeah.
repeat that? So
Yeah.
the Z is staying where it is, right?
Okay. Yep. And then as this thing, right? So this is going to rotate that everything around, right? So as that's rotating around, then Y was pointing this way, and then where's it going to point just a second later?
Maybe to the right, or I guess kind of hard to do this without being in person, but yeah, a little bit more the right.
Okay. So which direction is that?
Minus X.
Yeah, it's going to be basically in the minus X. Do you understand that?
Yeah.
Okay. And how does that work out with your cross products?
So it would be Y cross. That makes sense, right? Because it'd be like Y cross.
Well, what's making it change? So were you able to watch that? Did anybody get to watch that video I made? So I put the link, and did anybody get the email I sent out?
Yeah.
Okay. So if you go in, the video is a little longer than I like to do usually, but I try to go over a lot of this stuff in it. So that could probably help you out a decent amount, I hope. So nobody else has watched it yet?
I guess my specific question is, I understand part A with the velocities.
Yeah. And
then when you do the product rule to find the acceleration, is that correct?
Yeah.
Okay. And then I can cross things out because I know that, a frame like the Z doesn't change direction. So I can cross like the K dot out or Z dot out. I guess my question is, when I'm left over with like a theta dot, J hat dot, how do I interpret that term? Like, how do I change that into something that I can work with the J hat dot? I was kind of talking at the end of class about this, I think, but
yeah. So it's again, what's making that change, right? So if we have, the question is, and I tried to maybe make this a little different when I did this video, and I think that can help you out too if it's still a little fuzzy. But basically, you're saying this is the capital omega that's making it change direction. right? So remember this, and then what we did with that time derivative of a vector thing, and again, I'm sorry, but my my pen stopped working for whatever reason. So this is now a capital omega cross Q, and in this case, Q is the J, right, is the J that you're wanting to know how is that thing changing its direction, right? And then the capital omega is, well, it's really, the question is how is that affecting it? And well, it's omega naught in the K, right? And then we say that's what's changing the direction of J, right? Because you were saying it's the J dot, right? So really all we're saying is omega naught K cross J. And in this case, Q was just equal to J, right? But if we wanted to, we could even just throw in the, the fact that it's the theta dot, okay?
Okay.
Or the P.
That makes a little more sense, yeah.
Yeah, so what is K cross J?
Negative I.
Yeah, and that's basically what you have up here.
Okay.
Right. So
yeah, I
if
think the P equals negative theta kind of threw me off a little bit. But I remember you said it wasn't a double negative, right?
yeah,
Okay.
and that's what I changed. Yeah.
Okay. Thank you so much.
Okay. Yeah. So this one should have been actually, once you get that, it should be hopefully the easiest one out of them. Yeah.
Right.
Especially now that we went over it. Okay. More questions. Yeah. So let's look at number 5, and that's going to be. Oh, it's just not. All right. Technology is great, except when it's not quite working. Let's see if I. Okay, so. Sorry, it's the screen's frozen up now. Well, let's just see if we can't draw it on here, and then. So basically, you've got this. Jeez. Sorry about this again, you guys. Like I said, somehow my pen's. I'm using the mouse now. All right. So you remember we did the rock crusher type of problem? That's where we had basically. It's kind of similar to this, but on this end we had a bar, and then we had the disc on the end. Remember that?
Wait, are you doing number 5 now?
Yeah, we are. And
Okay.
I can't, for some reason, it's not letting me advance the screen. I don't know if any of you guys can do it or not. I don't think so. Usually you should be able to draw on the screen, but I don't think you guys can advance it, right? Like I say, it's not even letting me. What if I choose a mouse?
Did you see that?
Yep. Yeah, in fact, lots of times I'll ask you as we're working through, to draw the free body diagram. Oh, wait, there we go. So I don't know what happened there. Let's see. Why did that's really odd that the drawings would stay on there too. Let's see if I can erase this now. Okay, so can you guys see all the drawings, annotations that I'm erasing? Were those on your screen too?
Yep.
Okay. Yeah, pen's still not working. Shoot. Okay, so if you remember how that guy, I guess I shouldn't have done that one. Let's see. If you remember how that one was done, right, then we basically had this disc out on the end, and then this was stationary there, and it was going around, this guy, and then remember this was rotating in a certain direction as well, right? So for this, we can see the direction, that this thing's rotating around, right? So that means which direction is it going to go around as it kind of rotates?
Right.
Yeah. So it's going to go also around this big one, right? So it's going to go around the K hat, but in the minus K hat as well. Does that make sense, everybody? So it's kind of like, remember that wooden thing that I brought out to you, and the disc was rolling around and then also going around a bigger circle?
So So is it spinning in this direction too?
Yes, right, because it's just rolling along the ground. So it's fixed at O, and that's what it means when it said it's rolling in the XY plane. So the spin is at omega 1 you see, and then you have another rolling type of thing, like you can call it omega R or something like that if you want. Right, so maybe we call this omega R. Okay. Does that make sense, everybody? And that's going to be in the minus k hat. Okay, are there questions about that? Okay, so now, that means we're going to have two things, right? But which direction is the omega 1 in?
Y.
We've got some in the Y. Remember, that thing's slanted as well, right? So some of it's going to be in the Y, right? How much of it's going to be in the Y?
Cosine 45.
Yeah. Okay. So, in fact, let me see if I can. You know what I actually kind of recommend you do is make a big old triangle type of thing, right? So we can do like this, okay, and then okay, somebody's got a little bit of noise going on too. If you can mute your microphone again for me, please. All right, so if we look at all of these guys, right, then this ends up being just kind of a lot of trig in the end, because if you look, this is really the R, right? That's our R, and then you've got the angles here and here. So what is that? What are those angles going to be?
22.5.
Yeah, so those two angles are going to be 22.5. Okay, and then do you remember how we did when we did out the disk problem in class? So when we did this problem that I kind of scribbled up on the left-hand corner, then if we call, say, like this down, this middle point, point A, right? Then it ends up. Do you remember with the wheel? If a wheel's rolling without slip, right? Then what is its velocity of its center?
Omega R.
Yeah. Does everybody remember that? That's for our wheel that's rolling without slip. Well, the thing is, that's really good for, remember when we had a disc that's rolling up on the top. So what we have to do then is really figure out what this height, I'm just going to call this height H, right? So that's really our height up, because this is point A now, right? That right there is like point A. Okay. So I have to use that H, and then I have to figure out, well, what's that direction's omega, right? Does everybody, so what I've done is try to say, well, what's the same amount from this disk, right? So if you look back to when we did this guy up here, right? And let me see if I can draw that a little bit better, because I can do some sort of shapes here. So if you remember, that was where we had this guy like that, and then we had right, we kind of had the rolling deal on the end, okay, and then this thing here was like the post. Okay, so then now it was rolling around. I don't remember exactly which way, but it was rolling like this, and then it was rolling the way it had to. So it's kind of hard to show that 3D. It's actually going to be going like into the board there. Okay, so do you guys remember that problem and can go back to look at that? Okay, so if you remember, then let's say that was omega 1, and that was omega 2. Okay. Then I think like that was an L, and then let's just call that an R. Okay. And so we figured out the relationship, and we talked about it being kind of like a gear ratio, where essentially omega 1, right, times L ended up being equal to R times omega 2. Does everybody remember that? So this is because, essentially this is like a tangential velocity where, that's just going around at omega 1 out at a distance of L. And then like we talked about just a second ago, a wheel rolling without slip is going to have an R omega. Questions about what I just said? Okay. So now you basically have to use this same thing that we just did, right? So we're going to have to use this, but we have to do it for something that's like standing up. So in this case, the L is going to be just this distance, right? The omega is going to be whatever we find out for this omega 1 from this type of relationship, right? And then this omega is going to be like what somebody said was omega 1 times the cosine of the angle. And theta or beta or whatever you want to call it. Okay, that's the one that's going to be coming out. So what is my total omega going to be composed of?
Omega 1 plus omega R.
Yep, so I'm going to have the omega 1, and part of it's going to be in the K hat, and some of it's going to be in the J hat, and then what's the omega R in?
Minus K.
Yeah. Okay, so you're going to add those three together to get my overall omega. So let me say that again. Basically, you've got to figure out with this cone, we're going to make it into this system up here, right? So we're really going to transform it into this system. And how we do that is by saying, well, this times whatever component of omega is there, right, is just like this. What on earth? Is just like, it's just like this guy up here. Sorry, gosh. And then this from here to here, right, is just like what this omega R is going to be. So you're going to set up another deal like this, but instead of omega 1, it's going to be omega R. And instead of R, it's going to be this H. And instead of omega 2, it's going to be whatever this omega 1 cosine beta is. So that's going to be your overall omega. And then what is it that's making this omega 1 change direction? It's this omega R. And that's what you use for the alpha. Okay, so it's mostly kind of a little bit of a trigonometric variation of the one that we did up here in class. Really, this is a better picture. Okay, more questions. So is omega R 2.4? No, this omega 1 over here is 2.4. This is the 2.4.
So omega 1, would omega 1 be 2.4 times cosine of the 22.5 J plus sine 22.5 K?
Yes, that's what omega 1 is.
Okay.
Do you want to repeat that?
Yeah. Omega 1 would be the magnitude of 2.4 radians per second times the cosine of 22.5 in the J hat plus the sine of 22.5 in the K hat.
Yeah, see, because that's going really around this axis here is the direction of that omega 1, right? It's going all the way out like that. Well, what direction is that? That's half of this 45 degrees. So that's why it's going to be cosine of it's in the y hat direction here, and then sine part of it's in the k hat. Okay.
Mm-hmm.
Okay. So then let's take a quick look at number 6. Yeah, so Ben, we actually went over. I'm recording this, so for the code for that problem 3, then I'm gonna let you go back and take a look at the recording for that.
How do you do that?
Do what? Sorry.
Go back and watch the recording?
Yeah, so I'll post it under class 7 for the recording. This is the first time I actually was able to figure out how to log in the right way, because this is a new program that we're using, and as you can see, there's still some I may have to try to use a different thing with my pen. Maybe I can do OneNote or something. Last time the pen didn't mess up, but I didn't have the ability to record. So, and I don't know why it's keeping all the ink things on there. Okay, so now it's not letting me. It's frustrating. Sorry. So now it doesn't want to let me. Let's see. What can I do? The mouse. Okay, there it goes. So let me see if I can erase everything again. All right. So if we look at this one, right, then this isn't too much different. What should this kind of remind you of?
The stuff we do in class?
Well, yeah. Do you remember the one that we were starting with the motor housing? Remember how we had the gamma that was just sitting up there? So I was showing you in class where we had that kind of motor housing where it was here, and it was, I can't remember if it was really a sander or whatever, but is that ringing a bell? And that was rotating.
Mm-hmm.
So it was rotating on something like this, and then it was also rotating, I think, along an axis, right? It was on some sort of platform, so it was rotating about this axis too, right? So it's pretty much exactly the same problem. And like I was telling you before, when you start to really process these and work through more and more, then you start recognizing how similar these things are, and then that's when it really starts to click. So in this one, right, it's kind of a little bit even like the not that different from the one we just looked at with the cone, but in this case, the omega 1 is going up at this direction, right? So that's the vector, and is it changing its direction?
Yes, it is.
Yeah, so the omega 2 is going to be making it change direction, right? And omega 2, which direction is its vector?
Forward in the T.
Yep, so it's going to
Or
be,
V hat.
but I think in looking at how it's going, it's looking like it's an omega going down. Does that make sense? Is that how everybody else sees it too?
Mm-hmm. Why are you drawing that vector in the minus Z hat?
Because I'm doing my fingers. I'm curling my fingers around like where the omega 2 is.
Okay. Okay.
Okay, so now basically you're just going to work through, and you have to find the velocity of that point P. You're going to find what's a good reference point to find for P. So basically, right, this thing's on this kind of whole housing, like that whole thing is rotating around with omega 2, and then this is like a propeller, right? This AOP, you could think of it a little bit like a propeller, and that's spinning around with that omega 1. Right? So does everybody see that? So this whole thing is going around like this, and then the propeller up here is also spinning, like there in that path that you can see. Okay, so then what you have to do is, we want to know the velocity of point P, so then we find kind of the closest reference point that we can. So what point would that be? What would be a good point to refer it to?
Point A.
Yeah, so we're going to go to point A. So we're going to do velocity of P is going to equal velocity of A, right? Plus we've got the omega cross R P to A. And then we have plus the V rel. Okay. And in this case, do we have any difference or any relative term between A and P? Okay, so if I've attached my coordinate frame out at the end there, and rotating around with the propeller thing, then the VREL is going to be 0. Okay. So the omega 1, in terms of the components, you just end up having to figure out, right, you've got this 2.4 feet, and then you got the 1.8 feet there as well. So let me see what I ended up doing. Did we not give you a... Oh, well, this is a right
For the
angle.
last velocity,
Yeah.
for the last velocity vector, it's VP/R. What's R?
Oh, sorry, rel.
Oh, relevant.
Yep, sorry, I didn't finish writing that, and I'm not writing so well with this. Yeah, so basically you can complete that triangle. I'm sorry, Megan, do you see what I'm saying? So that 2.4 going up, and then the 1.8 is going to be completing that full triangle because point P is directly over point O. Okay, so that's your VP type 1, right? So basically point A is rotating, about this. So it's going to have a tangential type of velocity, right, of its own. So point A's definitely got a velocity that you can figure out. And then you do the P relative to A is going to be this term because we just said that's 0. Okay. And then how are you going to find out the alpha, right? Because you're going to need to know an alpha or really like a capital omega dot. So then you're going to have to do the same type of thing as we've done in class, right? So you got this omega 2 plus the omega 1. You got to write those all out in IJKs, and then you're going to take the time derivative. So I do think that little video I posted is going to help you figure out these alphas. So please try to take a look at that, and I think it should be useful for you. Okay, so I think we've actually kind of talked about all of these except for the park deal. So hopefully that was helpful, and I'll try to figure out what went on with my pen, but I will see. I'll see what I can do to post this because I think it should end up just being a link, and then I'll put it up on the class 7. Hopefully I can figure that one out. And I'm going to so you guys can't go back and forth, right, between different pages. Disable audio. Okay, yeah. The other one I used to do, I could control and say, look, that you guys can go back and forth between different white pages. So, so I'll have to see if there's a way to ever let you do that again. But okay, so good luck. I will. I'm going to stop the recording and then I'll try to find that.